For observing the sunspot, we have covered telescope and we are allowing only a limited light to enter the telescope through this filter. So this is our 11-inch refracting telescope we are going to use to observe the sunspots, and for recording the images we'll be using a camera that is fitted to the telescope. So let's take the telescope out.
So Joe, when we observe the sun through the telescope, I had seen such kind of an image. So what does this black kind of thing mean?
Right. So what we saw in the telescope is these things called what are called sunspots. So these sunspots are relatively cooler areas on the surface of the sun compared to the rest of the region. And I say cooler because those regions are only at around something like 4000 degree Kelvin, while the outer regions are something like around 5500 Kelvin. So it's not really cool as in what we are used to in our normal life, but for the surface of the sun, it is relatively cool. And what is happening here is that, you know, the black body, when some object radiates energy, the amount of energy it radiates is proportional to the 4 power of the temperature of the object. So what we have here is a cooler surface which is emitting much less thermal radiation compared to the surrounding regions. That's why you see these continuous image that these spots looks darker compared to the brighter surroundings. And so these are effectively those cold spots on the surface of the sun.
So what is the reason for this?
Yeah, so what is happening here is that like the sun, as you all know, like at the core of the sun is creating energy by nuclear fusion, like what is shown in the diagram over here. And then it sort of radiatively comes out. But at the surface of the sun, the energy comes out via convection. So convection is the same phenomena you see when you boil water on a stove. Like you would have seen those cells of water going up.
Yeah, and this glue sound coming.
Right, and going up and down like that, full circulation. So that's exactly how the surface of the sun is. It's also flowing, gas is flowing. And that is the process which takes the radiation or the energy at this lower level of the convection zone to the surface that we see on the sun. And now, if there is, like, say, a strong magnetic field, and if there's like a slight bit of ionization, you know that a charged particle will experience a Lorentz force when it goes to a magnetic field. So it cannot freely flow the same way it would flow if there is no magnetic field. So what happens is if there is a strong magnetic field in one of these regions, it sort of suppresses this convection, this sort of like the rising of the hot air and going down. So that suppression of the convection prevents that particular part of the sun to be receiving less heat radiation from the layer below it. So you basically have like a cooler patch on the surface of the sun because of the suppression of the convection coming from it. And this effectively causes that region to have lesser temperature than the sun. So the reason why we see these dark spots is because those are the spots with very strong magnetic fields, and those strong magnetic fields is what is causing those regions to be cooler and resulting in the sunspot.
So now this, do this stays forever on the sun?
So no, so they sort of evolve over time. What we see that these sunspots that we see right now, they will be there for like few days to weeks time scale, and then they go away. But there will be other sunspots coming up right now. And it's very interesting that these sunspots are not always present on the surface of the sun. They come and go in a something called 11-year solar cycle. Like if you had gone and looked at the sun 6 years ago, you would see a very pristine, clear sun. You won't see these many spots like we are seeing right now. So they sort of periodically come and go, and they evolve over time. So there is this. We are right now at one of the coming towards the peak of these current solar maximum, where we have the maximum number of suns.
So while we study about this, is there any use for us? Like, and affect our lives?
Yes, this has serious implications because sunspots are actually representation of how active the sun is. So the number counts of the sunspots are the best proxies for the sort of the activity of the surface of the sun. And when you have an active sun, so the sun surface, even though the core is actually very stable and smooth, there are quite a lot of turbulent things happening on the surface of the sun. Like for example, there are these coronal mass ejections which throws out matter, and there are these winds, the solar winds, which sort of like continuously blowing from the surface of the sun. And if more active a sun is, more chances of these CME ejections, etc., getting launched. And if that happens to be in the direction of one of these major CME ejection, we will be showered with lots of charged particles and so on, which are obviously bad for all of our satellites. So you will have to basically switch off all your electronics so that you don't fry them on board on the satellite. And it's not just on the satellite, like even on the surface of the Earth. So India, because we are more closer to the equator, we are sort of protected by the magnetic fields of the Earth. But the magnetic fields protect us by channeling all of these charged particles falling on the surface of the Earth along this magnetic field towards north and south pole. So for the countries which are in high latitudes, like North European countries or like Canada and all, they will have major disruptions of the charged particles coming in there. Like they will have like electric grid failures, transformer blow up, and all sorts of things. So you have to be aware of when this is going to hit us and take precautionary measures. So that is why like there are already these satellites, we are always pointing towards the sun so that we know there is a CME is coming towards us and we can take precautionary measures, whether it is people on the International Space Station or satellites. So there are major implications. It also, of course, have implications on the weather also in some sense.
Yes, so what are the ways to observe these things? Can we say in this time this will appear earlier?
Yeah, so I mean, because light travels fast, the earliest we will know is by the optical electromagnetic imaging. So we have these cameras which are looking at it, like for example, SDO telescope. I'll show you an image later. So there, when we see it optically, we see this radiation, this activity happening. So because CMEs are like protons and all, they take more time to reach Earth. So what we see optically is like photons that we detect of this activity. That, and we then measure what angle it is, so we can predict whether Earth will be in the path or not, and then we can take precautionary measures.
Okay, you said it will not stay there forever, but it will appear and disappear in time. So, is this appear randomly or?
No, so we don't fully understand why exactly 11 years. Like we don't have the model tells you exactly these 11 years or 12 years. But we do have a overall idea of the phenomena that is happening in the sun. So this is understood by the solar dynamo theory. So it is what is happening is a fairly simple concept. Initially, you can think of it like something that is shown over here. You have these magnetic field, just like in case of our Earth, entering at North Pole and exiting at South Pole, like sort of we see a colloidal magnetic. But a sun, unlike Earth, is a fluid and it rotates at different speed at different latitudes. Like for example, the equator rotates much faster than the poles. And what that happens is that as I said earlier, because the magnetic fields are sort of pulled by a slightly ionized medium, the magnetic field is. So when the fluid moves, if it is slightly ionized, the magnetic field also gets pulled with it. So as it rotates, you can see these magnetic fields get sort of stretched near the equator and they start getting twisted around the sun.
This looks like a rubber band winding around a sphere.
Yeah. So that's exactly true. Magnetic fields in many astrophysical scenarios behaves exactly like a rubber band. In a slightly ionized medium getting stretched, it can behave, stretch, even recoil. Exactly all those properties are there. So this sort of continues, and as the sun rotates and rotates, you end up with sort of like really twisted magnetic fields. In sort of like you start having this sort of toroidal magnetic fields, which goes in this direction, as you can see. But while this is happening, there's of course convection happening on the surface of the star. So when you have a horizontal magnetic field, convection can basically cause buckling of these magnetic fields sort of coming up, which is what is shown over here. So you can see the magnetic field sort of leaving the surface and sort of going back. And these high concentrated regions where the magnetic field is perpendicular to the surface is either leaving the surface or coming back into the surface, or where the sunspots appear, because that's where the concentration is. And that is what causes sunspots. And then after this, so this takes almost like 6 years for this entire process shown over here. Then it again goes back. This toroidal magnetic field sort of collapse on itself and sort of ends up going back to the toroidal magnetic field. But then the north pole will be magnetic north pole will be on the southern side, and the magnetic south pole goes in the direction. And then it again does. So it's actually a 22-year cycle for the magnetic field. Half of that 11-year cycle is what we see in the sunspot as that. So that is what, and that's our present understanding of how these sunspots occur.
That's all about my doubts. Thanks.
Thank you.